Hey everyone, and welcome to Next Gen Manufacturing. Today, we're diving deep into a material that's pretty much invisible, but it literally builds our modern high-tech world. From supercars to green energy, it's the secret ingredient you've probably never even heard of.
I mean, just look at this. A massive wind turbine blade, or the sleek body of a high-performance car. These things have to be unbelievably strong, but also super lightweight. So how do you even make something like that? What kind of material can possibly do that job?
Well, the answer lies with the true unsung hero of the manufacturing world. It's a material that starts its life as a simple liquid and then transforms into something extraordinary. So let's pull back the curtain.
Meet unsaturated polyester resin, or UPR for short. The best way to think of it is as a versatile liquid backbone. In its first state, it's kind of like a thick syrup, but with just a little bit of chemistry, it becomes this rock-solid foundation for some of the most advanced products on the entire planet.
So what makes this stuff so special? It's what's called a thermoset. And the easiest way to get your head around that is to think about baking a cake, right? Once you mix the ingredients and bake it, that change is permanent. It's irreversible. You can't turn that cake back into eggs and flour. And that's what gives it its incredible strength and heat resistance. It's totally different from other plastics that you can just melt and reform over and over again, kind of like freezing and melting ice.
Okay, so let's get into it. How is this wonder liquid actually made? You can really think of it like a very precise chemical recipe, and it's cooked up in two main stages.
First up is a step called polycondensation. That's where the base polymer gets created. And the second step is dilution, where that polymer is dissolved into another reactive liquid to get it all ready to use. It's a simple two-step process, but the real magic? Well, that's in the ingredients.
These right here are the building blocks. During that first step, polycondensation, chemists are linking together different acids and glycols. A good way to picture it is like linking different types of paper clips into these long, flexible chains. And the different clips you use are what give the final material its specific properties, like whether it's more flexible or more rigid.
So once those long polymer chains are formed, they're dissolved in a reactive diluent, which is usually styrene. And the result is this viscous liquid we started with. It's a perfectly prepared resin, just full of immense potential, waiting for the signal to transform.
So, we've got our liquid, but the absolutely crucial step is getting it from that state to an incredibly strong solid. This is where the real transformation happens. This is where all that potential becomes pure performance.
So how does this syrupy liquid lock itself into a permanent, super strong, solid structure? The answer is a process called curing. Curing is basically a massive chain reaction. Those long polyester chains and the styrene molecules, they all start linking up with each other, creating this incredibly dense three-dimensional web. And that cross-linked network is what gives the final material all of its strength. But this reaction doesn't just happen on its own. It needs a little push.
Now this is what's really cool. Manufacturers have this amazing toolkit they use to control this powerful reaction. First, they add an initiator. That's basically the spark that starts the engine. Then, an accelerator acts like the booster, controlling how fast the whole thing happens. And just as important, an inhibitor acts as the brakes, making sure the whole reaction doesn't kick off before everyone is ready. It's this precise control that makes UPR so incredibly versatile.
Okay, now that we know how it's made and how it works, let's take a look at the incredible world that's built from this stuff. And believe me, you will find it everywhere.
In the marine world, the hulls of countless boats, everything from small pleasure craft all the way up to larger yachts, rely on these polyester composites for their strength, their lightweight, and of course, their resistance to water.
And in transportation, it's used for lightweight body panels on sports cars, really durable cabins for trucks, and all sorts of structural parts that improve fuel efficiency without ever sacrificing safety.
When it comes to our infrastructure, it's absolutely essential. Those massive corrosion-resistant pipes and storage tanks that hold everything from our water to industrial chemicals, a lot of them are made from these composites. Why? Because they simply don't rust, and they can last for decades.
And this just brilliantly illustrates its role in next-gen energy. The enormous blades of modern wind turbines, and some of these are longer than a football field, they are only possible because of the incredible strength-to-weight ratio of these materials.
But here's the real secret to that incredible strength. See, on its own, the cured resin is strong. Yeah, it's pretty good. But when you reinforce it with fibers like glass or carbon, creating what we call a composite, its strength just multiplies exponentially.
We're talking an increase of nearly 20 times. That is how you build a wind turbine blade that can withstand hurricane-force winds. So this material is truly a marvel of chemistry. But its greatest strength, its permanence, is also its greatest challenge. And that brings us right to the next chapter for manufacturing.
And here it is, the core issue for next-gen manufacturing. Remember that cake analogy? You can't unbake it. Once these thermoset composites are cured, you can't just melt them down and reform them like you can with a thermoplastic. So, what do we do with them at the end of their life?
Well, the industry is developing some really clever solutions. First is what we call material recovery. That means grinding up old parts and using the powder as a filler in new materials. Second is energy recovery, which is basically safely incinerating them to capture all their stored energy. And finally, some processes do both, using the waste as fuel and raw material in things like cement kilns. We're finding ways to give this so-called permanent material a second life.
Which leads us with this final crucial question for the future of manufacturing. We've become masters at creating these incredibly durable, high-performance materials. The next frontier is to design them to have a planned, sustainable end of life. Can we make materials that are not just built to last, but are also designed to disappear? Now that is the challenge for the next generation. Thanks for watching.